Okay, so we last looked at the different types of reactions with benzene, and now we need to apply those to synthesis, our favorite subject, right? So that means that we have to understand how to put a series of substituents onto a benzene ring. In other words, not just put on one substituent, but what happens when you put on the second substituent, maybe even the third. So let's start with some basic concepts here, okay? If we've been talking about the electrophile for a while, that means that benzene's acting as a nucleophile, right? So things that make benzene a better nucleophile are going to make this reaction speed up. And things that allow this to work as a poorer nucleophile slow this reaction down, right? Okay? So a nucleophile is something that is electron-rich. That means that this has to do with electrons and electronegativity and a whole bunch of other stuff here. And there's two major categories that we really look at excuse me, when dealing with these. The first is just inductive effects. So this is something that we've talked about before. It's a change of electron density due to electronegativity and polarizability. So imagine this is sort of like a tug-of-war of electrons. If there's an electron or oxygen or something like that that's pulling electrons to one side, then it can pull electrons out of a ring or something like that. But truth be known, when it comes to benzenes, this is not the major player. The big player, as we've seen before, is resonance. And this is going to spread electron density through resonance. Okay, here's the big thing, and I highly encourage you to try this on your own, because this shows you how to do all kinds of resonance structures, but this is very key in understanding what we're going to talk about today. In this situation, we've got electrons on the atom that's connected to that benzene ring. If you look at resonance structures, these electrons could be donated down into that ring, pushing this up. That gives you this resonance structure. That means that there's electrons that just went into the ring, or they were donated into the ring. Then you can do resonance structures here, resonance structures here, and then go back to this guy. Okay, so we just put electron density into that ring. That should make it a much better nucleophile, right? Reacts faster. Okay. On the opposite end of that spectrum are electron withdrawing groups. These do not have an electron pair here. And you might say, well, why can't I take this down? Well, there are 1, 2, 3, 4, 8 electrons around that oxygen. You start pulling these guys down, oxygen no longer has an octet, he ain't happy. And therefore, that's just not going to happen. So these electrons are forced out of the ring, leaving behind a positive charge. Electrons would move, and that positive charge goes to, wow, it goes to the exact same places that negative charge went to, just as a pattern there. Now, if you have a positive charge in the ring, is he going to want to go and react with something that's positively charged as much? No, he's not. So that means that if we have something that's donating electrons, that might make this reaction happen faster, and things that are withdrawing electrons might make this reaction happen more slowly. So if you're an electrophile, and let's say that this is what you've got, right? You've got electrons, you're donating them down in here. They exist in these three places, and this is sort of what the hybrid looks like. You've got a negative charge at the ortho and para positions. If you're an electrophile, you say, ooh, I want to go there or there. Now, actually, I prefer here because, hey, there's plenty of space here, but I can go either of those places. Therefore, things that have electron donating power put electrophiles on the ortho and para position. Now, let me just state, that's relative to where this substituent is. So if I have something that is on this oxygen and I'm going to react that with another electrophile, it should go to here or here. Okay? In contrast, if I have something that is electron withdrawing, then I'm going to end up with positive charges in those same positions, and the hybrid would have partial positive charges here, here, and here. So if you're something that's positively charged, you're going to not want to go to where the other positive charges are, right? Therefore, this will go to the meta positions, both here and here. So let me show you this in general. Let's say that we have what I just drew up here. We've got an OH, and I'm going to do this with Br2, FeBr3. Then what I should get as products should be an OH here and here, right? Notice I didn't draw one over here, but yes, that's the same thing. At the other ortho position is just flipped over, right? Okay, on the other hand, if I start with something like this, and the nitro group is NO2, and I were to do Br2 and FeBr3, then I should end up with the Br at the meta position right there. Okay. So when we're doing synthesis, as you might imagine, it makes a big difference as to what order you do things in, and you got to figure out what goes where and what's going to direct where. So here's the basic chart. We're going to have these guys be strong activators. The reaction will happen quickly, and they're going to go ortho-para. These are also ortho-para directors, as are alkyl groups. Alkyl groups actually donate inductively. Let's skip halogens. Let me come back to that in a minute. Start at the bottom. These are strongly deactivating compounds, and these are moderately deactivating compounds. These are going to be our meta directors down here, and these are going to be ortho-para directors up here. Okay? Now, let's talk about patterns. All of these have heteroatoms with an electron pair on them that they can donate into the ring. These do too, it's just that they have a C-double-O bond next door that's kind of pulling the electrons up as well. They can also resonate up that way. Alkyl groups, and then halogens. Halogens inductively withdraw electrons, but they can form resonance structures, and since resonance structures are king, that's the reason why they are ortho-para directors. Regular hydrogen would be here though, okay, so we're sort of in the middle, which means that this is a slow reaction, but it'll still go ortho-para. Let's talk about the deactivators. These guys either have a positive charge or they don't have any electrons free whatsoever. And notice that all of these are directly connected to a C-double-O bond. So these heteroatoms have a positive charge. These are going to be very strong deactivators. And if you draw the resonance structures for these, except for CN, these are going to have a positive charge on that heteroatom, depending on how you draw. Well, not necessarily sulfur, but. And then we've got the C-double-O bond here. So there's a pattern here. Know the pattern, and really and truly, if you can figure out which of these two extremes you're on, for most substituents, either you're going to put them in the ring, electrons in the ring, or electrons come out, then you can determine if this is going to be an ortho or para director. And then also know that alkyl groups direct ortho-para, and halogens do as well. Okay, thank you very much.